My name is Dr. Satyanarayan Rao, and in this video we will explore the fundamental difference between classical and quantum information. We will also understand qubits and see how they are represented on a Bloch sphere. So we know that the classical information is straightforward. It uses bits that are either zeros or ones, and we can store this information say on a USB drive or a DVD or flash drives. So when we store classical bits on a USB drive, it remains stable. We can read it multiple times without changing it. Let's say we have an image. We can apply some algorithms like a Fourier transform or any sort of classical algorithms, and the image that is being in the USB stick remains intact, and it's stored as zeros and ones. Like it could be like Fourier transform or anything to our classical information that is stored as zeros and ones, which we refer it as bits. We may introduce some errors, and all these errors in the processing of this information, which is zeros and ones, are obeying the classical laws, and hence they are predictable. For instance, we can have some kind of random Gaussian error, or we can distort in a predictable way the information. That's what I mean. And once we do some error or processing, we can always go back to our pen drive to check our original information, and we can measure it indefinitely without altering what is there in the pen drive. And let's imagine if we have a quantum pen drive or a quantum memory, which will now store something called as qubits, which means it will have both zeros and ones, or ones and zeros at the same time. So the quantum information is fundamentally different. A qubit can exist in both zeros and ones because of a property called as superposition. And this leads to two crucial differences. While a classical bit is 0 and 1, for sure, it doesn't change the way. Once we store an image of a person, it doesn't change. But a qubit will exist in multiple states at once. And unlike classical bits, measuring a qubit changes the whatever we have stored. It's like we do not know what is being stored here, and when we measure it, the act of measurement can also change. Let's say like a quantum analogy of a pen drive is, suppose if we store an image and we do not know whose image is there, and depending on who opens the image opens. Like if a dog opens the image, an image of dog appears, or depending on who opens, the information can change. So this unique behavior requires entirely different sets of algorithms and approaches for quantum computing. So let's see another difference between the classical and quantum bits. So with classical bits, if we have n bits, let's say we have here n equal to 3. So if we have 3 bits, we can exactly represent one integer at a time. For example, if we have a 3-bit system, 000 can mean 0, or 001 can mean 1. So each state represents exactly one integer at a time. In a quantum computing, because of superposition, what we have is n qubits can actually represent all possible integers here. We represent such system mathematically as psi here, which represents our quantum state, and here Ci represents the amplitude of finding a system or getting a particular integer value. So here this I value represents all possible integer system here, and the Ci is the amplitude probability of finding the system in a particular state I. And so when we measure this n qubits, we will not only get one of the possible integer value, but the act of measurement itself influences what we measure. So like we are forced to act as if all the possible integers are there in a particular bit. But even though we know that what we actually measure is a particular number, when we measure we get a particular number, but it could be anything. So let's say, like, before measurement our quantum state was something like this, where we had two possible bit in the 0 state with a probability of alpha, and in the first state with a probability of beta. So after measurement we can get zeroth state with a probability of probability amplitude of alpha square, and we can get either one of these measurements. And for a 3 qubit system that we saw earlier, that means we will have a quantum state something like this, with different probabilities for each of these states. We will have C1 that has 0, 0, 1, and similarly we will have till C7, which covers the last bit. So but when we measure we will only see one of these states, but we can't predict with certainty which one we will get. Even more interestingly, we can't even be sure if what we measured was the state that existed before the measurement. For example, let's say I measure the 3-bit qubit system and I get number 5, but I never know before just measuring it was 5. It could be some other integer, just that we measured and it came out as 5. And so as a summary, 3 classical bits, if we have 3 classical bits, they are at one state at a time, or they can represent one integer at a time. But if we have 3 qubits, it means we have superposition of 8 possible integers, and when we measure it we get a one state. So while this might sound impractical at first, it's precisely this behavior that gives quantum computing its advantage. This ability to process multiple states simultaneously enables certain quantum algorithms to solve certain problems exponentially faster than classical computers. So actually there is one more difference between classical and quantum bits or quantum systems. Let's take a simple analogy. Let's say I am filling a job application, and the order of question that I am asked in a job application should not matter. For example, if I am asked, am I detailed oriented, or am I creative, or can I work under pressure? All these questions, the answers should not be dependent on the order in which they are asked, and they should be consistent regardless of in which order these questions were asked in the questionnaire. But interestingly, researchers have found out something fascinating, that human decision making sometimes behaves more like a quantum system, because in a quantum system the order in which we probe the system can disturb the system, and it depends. In a quantum system, for example, the order of the query is important, whereas in a classical system it's not important, because in a classical system zeros and ones are fixed, and definitively either it is 0 or 1, and it's definitively either I am creative or I am not creative, and I can either work under pressure or I cannot work under pressure. Ideally this should be the case, because we think a classical system, the questions have definite answer, and the order of questions should not change the outcome. And scientists have found evidence that our brain might actually perform quantum computations, which could explain why we can still outperform supercomputers in certain tasks. For example, with today's large language models, we know how complex it is, how power consuming it is to train even a simplest model, but our brain consumes the energy from a pasta or maybe a bowl of soup, and we can perform similar training our neural network. And so sometimes also when we are in a state of making an important life decision like choosing between different career paths, we are not just uncertain, our minds might be operating more like a quantum system with multiple possibilities coexisting until the moment of decision collapses our quantum-like state into a classical outcome. For instance, when we are applying for jobs, we can parallelly imagine to be in different roles on different job applications that we are applying, but we will collapse to a particular role once we get an offer letter. But this is something similar. So, having understood the difference between quantum bits or the qubits and the classical bits, now we will see how we can represent the qubit in a mathematical way. So, we can represent the current quantum state of a qubit as a superposition of zeroth state and the first state, and it's represented by psi, and the alpha and the beta are complex probability amplitudes. And now we may think why we need alpha and beta as complex numbers, because the quantum states are like waves. We know that the particle like electrons can behave both like waves as well as a particle. So for a wave we need amplitude and phase so that they can sometimes constructively or sometimes destructively interfere, and that's why we need complex numbers. And when we take the absolute magnitude of alpha and beta and square it like this, we get 1. So this is called as normalization, and we can also represent alpha and beta in this way with the amplitude and the phase term. And the relative phase difference between alpha and beta allows us to have the constructive and destructive interference. So we will have some relative phase difference. And if we see the normalization where the amplitude of alpha and beta sums up to 1, this is actually the equation of a circle. And since we have alpha and beta as a complex number, we have two parameters. One is the amplitude, the modulus of alpha, as well as the phase. So we have two parameters. So to represent them, we need a sphere, actually some sort of this, where we can represent both phase and the magnitude of the complex probability, and this is called as the Bloch sphere, as we see in here. So here we start with our quantum state alpha and beta, having two states 0 and 1, and where alpha and beta are complex numbers, and we can represent in like this with amplitude and phase. And by using Euler's identity, we can write we can denote exponential function as sinusoidal functions. And so the same psi can be now represented as cos term with 0 state, and in a phase with the sine term and in the 1 state, where theta ranges from 0 to pi and phi ranges from 0 to 2 pi. And this represents actually a sphere with two angles, theta and phi. So now with this equation, the state of a qubit is a point on this sphere. It can be any point on this sphere with the superposition of 0th and 1st state. So in a Bloch sphere, the north pole here corresponds to the 0th state, while the south pole here corresponds to the 1st state, which means now we have a collapsed state similar to a classical system, where if we measure qubit on this point or this point, we know that it's in the perfect 0 or 1 state. But any other point, the qubit can come here or here. This represents a mixed state with with both zeros and ones. For instance, if we measure a qubit on east or west poles, this means we have an equal probability of having 0 or 1, but with a different phase. It means that if we measure a qubit here on the east pole, it means it can either be 0 or 1 with equal probability, and it's the same in the west pole on the equator, but the difference is they will have different phase, and it makes how that this qubit will interact with other qubits, because it has a different phase as compared to a qubit here. And so this is what a Bloch sphere, we can represent a qubit as a vector from the origin to any point on the sphere, where north and the south pole represents the classical state, where the state has collapsed to perfect 0 or 1, or we can call it as ground truth or the default states of a qubit. And in summary, we have explored the key difference between classical bits and quantum bits. While classical bits are zeros and ones, a qubit can be in a state of 0, 1 or any superposition in between, represented as any point on this Bloch sphere. The Bloch sphere allows us to represent qubit state visually, including its probabilities and also their phases. Phase is required because we need to have interference effect, which are inherent to quantum systems. And the north and the south pole actually represents the state of zeros and ones, while the equators, especially the east and west poles, represents a balanced superpositions with a phase difference. Because qubits are sensitive to even tiny disturbances, they can easily lose their information due to errors from outside. And this is where quantum error correction is a hot research area, where researchers are working to preserve and protect these fragile quantum systems. So as a summary, if we have a 3-bit system, like starting from 0, 0, 0 to 1, 1, 1, it can represent, as we saw earlier, any integer between 0 to 7. But a 3-bit quantum system doesn't just hold a single state, it can represent all possible combination of those bits due to the superposition. And the ability to hold multiple states at once makes quantum computing especially promising in certain applications like molecular interactions, in chemistry or material science. And however, like a quantum state, when we measure it, we know that it can impact the quantum state. And so if we are able to preserve the quantum state long enough before we measure it, we can extract useful insights from it. And this is all about the quantum error corrections, which is a hot research area, where we are actually making that the quantum states are highly sensitive to their surroundings. So researchers are developing methods to stabilize them without disturbing the superposition. And in this way, we could actually process large amount of information in a parallel way. In our next videos, I will try to go a bit deeper into the world of quantum computing by exploring some basic quantum gates. Just like we have classical gates like NOT, AND or OR gate, we do have some quantum gates. We will start with the simplest quantum gate called as Hadamard gate, and we will see how these gates work and how they create superposition and how we can implement them in a simple way. And I will also try to get some exercises done in the Qiskit Python library by IBM. It's a tool for experimenting with quantum circuits, and we will see what we can do in the future video. So far, I hope you have understood the concept of qubits and classical bits. Thanks for watching, and remember to keep learning and enjoy life. See you next time.